Good evening, everybody. Today, me, Manesh Srivastava, and my team partner Jayanti Yadav will be presenting a comprehensive study of insertion sort with real-world application, which is sorting the phone contacts. Discussing the insertion sort algorithm, a fundamental and practical method for sorting data based on the findings in a detailed study. How insertion sort works. At its core, insertion sort is a simple and intuitive comparison based sorting algorithm. You can visualize it as a sorting hands of playing cards. The algorithm works by building a sorted portion of the list, one element at a time. It picks an element from the unsorted part, which is called the key. It compares the key with elements in the already sorted sublist to its left. It shifts all the larger elements one position to the right to create a gap. Finally, it inserts the key into the correct position. This process is repeated for every element, gradually producing a fully sorted list. There are a lot of real world relevance and examples. While its simple nature might seem limited, insertion sort holds significant real world importance, especially for handling data that is mostly sorted or arrives in small and incremental batches. Let me explain the pseudocode for the better understanding. The outer loop for I is 1 to n minus 1 iterates through every element starting from the second one, setting the current value as the key. The comparison index j is equal to I minus 1 starts at the end of the sorted sublist. The inner loop, while j is greater than or less than 0 and a of j is greater than key drives the process. As long as we haven't hit the start of this array and the element at a of j is larger than the key, we perform the shift that is a of j plus 1 is a of j and j we then move to the left which is j is equal to j minus 1 and then a of j plus 1 is equal to key which places the key into the open slot. Coming on the time complexity and space complexity, we know the insertion we get, the best case for insertion sort is big O of n, which is nearly the sorted list. The average case is big O of n squared, which is the random order. The worst case is big O of n squared, which is the reverse sorted. The space complexity of insertion sort is given as big O of 1, which is in place sorting. We get on to the real world example, which is sorting contacts on the phone. Perfect example is sorting contacts on the phone. If you add a new contact, the system uses insertion sort to efficiently place it in the correct spot without resorting the entire list. Let's walk through the steps of sorting a list of names. We can see the initial list contacts are Zakir, Anjali, Ramesh, Bhavya, Suresh, and Asha, which is the unsorted list. In step 1, Anjali is inserted before Zakir. In step 2, Bhavya is inserted between Anjali and Ramesh. Step 4, Asha is inserted right after Anjali, and in step 5, we get the final inserted list, which is Anjali, Asha, Bhavya, Ramesh, Suresh, and Zakir. And this is how it is arranged alphabetically.
Now we'll talk about the charts. First one is the runtime growth chart. So if we talk about this, on the slide we have a runtime comparison of insertion sort across the best, average and worst cases. We can see three curves. The best case line is almost straight and increases very slowly. This happens when the array is already sorted. In that situation, each element just gets compared once. So the time complexity is big of n. The average case curve grows upward much faster. This represents a normal unsorted data set. Some elements need a few shifts, some need many. So on average, the cost becomes big of n squared. The worst case curve is the steepest one. This happens when the array is reverse sorted. Every new element must shift all the way to the beginning, giving a full n square growth. So as n increases, we can clearly see the quadratic curve rising rapidly. This is why insertion sort is excellent for small inputs but becomes slow for large ones. Now, if we talk about the space complexity chart, this graph is extremely simple, just a straight flat line. That's because insertion sort uses constant space or big of 1 space complexity. It always uses the input array itself, the one temporary variable key. Even if the input grows to thousands of elements, memory usage stays constant. This makes insertion sort very memory efficient compared to algorithms that need extra arrays. Now, if I go to the next slide, now here's the executive summary. This executive summary explains the core idea of insertion sort. It builds the final sorted array by taking each element and inserting it at the correct position in the already sorted left side. It's just like sorting playing cards in your hand. Take a card, compare it with earlier cards, and place it where it begins. Insertion sort is stable, meaning equal elements stay in the same order, and it's in place, meaning it uses only constant extra space. The performance depends heavily on the input. If the list is almost sorted, it works in big of n time. But if the list is random or reverse sorted, it becomes bigger of n square. Because of this, insertion sort is perfect for small datasets or situations where we insert items one by one, like adding a contact to a phone's sorted list. Now, if I talk about the conclusion, to conclude, insertion sort's biggest strengths are its simplicity and its low memory usage. It is stable, easy to implement, and predictable. However, its main limitation is the big of n square. Worst case time, which makes it unsuitable for large or highly unsorted data sets. We mainly use insertion sort when the list is small, the list is already almost sorted, items are inserted one by one. Because its clarity and practical use on small inputs, insertion sort is an important algorithm to learn in computer science. Thank you.